Okay, in this video we're going to look at two questions. One is a past exam question and the other one is a question that's from your book. So these are both using the Winkler method and titration, and this question here appeared as a question one type question, and we're just going to focus on the calculations part of the video. So if you want to pause now and have a little read through the question, and then we can get stuck into it. Okay, so I'm just going to underline quickly the important parts. So what we have is the chemical reaction between iodine and sodium thiosulfate here. In these types of questions, you might be given one reaction, or you maybe have three reactions in front of you, but they've actually just given us the ratio here. So this is another important piece of information. It says that 4 moles of the sodium thiosulfate were required for every 1 mole of dissolved oxygen present originally. So they've actually given it to you in a sentence here, but oftentimes they might give you 3 equations, one after each other, just like this down here, and you'll have to work that out yourself. So the very first question, it says the average number of moles of sodium thiosulfate used in a titration. And when they ask you specifically for the number of moles in a specific amount of volume or in a titration, you're going to use first principles. So we're just going to take all the important parts out. So sodium thiosulfate. So I'm just going to write down all the information that I have about that. We have 3.1 grams. Of that substance per litre. The volume is 6 centimeters cubed. And for the iodine then, we have 200 centimeters cubed of the iodine, which is the volume. Okay, so it asks you to find the average number of moles of sodium thiosulfate used up in the reaction. So let's look at the information that I have about sodium thiosulfate. I have those 3.1 grams. I have the molecular formula, and it said in the question that the 3.1 grams was indeed made up into a litre. So I can use this formula, number of moles equals the mass over the relative molecular mass, to find out the molarity of the solution that was made up of the sodium thiosulfate. So I don't have the number of moles, so that's going to stay blank. The mass was used as 3.1 grams, and the relative molecular mass then I can work out by looking at my periodic table. So I have 2 sodium ions, 2 23s. I have 2 sulfurs, 2 32s. I have 3 oxygens. I have 10 hydrogens. That 5 times 2 is 10. And the hydrogen is 1 each, and I have 5 oxygens again. So that becomes 3.1 divided by 248, which gives me 0.0125 moles per litre of the sodium thiosulfate. Now it says the average number of moles used up in a titration, so that's in per litre. I don't want a litre. In the titration, the average amount was 6 centimeters cubed only. So I want 6 as a fraction, only 6 centimeters cubed out of the litre, which is 1,000 centimeters cubed. And I'm going to see how much moles are in that. So I'm going to multiply it by the molarity. So again, this is the amount of moles per litre, and I only want a fraction of that, so I'm multiplying it by the fraction that I want. And I'm going to get the answer then to be 7.5 by 10 to the minus 5 moles in 6 centimeters cubed of the sodium thiosulfate solution. And that's question 1 answered. The next question is the average number of moles of oxygen that release the iodine detected in each titration. So for each titration, we know here from this sentence here that 4 moles of the sodium thiosulfate reacts with oxygen in a ratio of 4:1. So I already have how many moles of sodium thiosulfate were used in each titration. And it says here in each titration. So 7.5 by 10 to the minus 5 moles was used. And if I want to find out how many moles of oxygen were used in each titration, I just need to divide that number by 4. So that's what I'm going to do. Take the 7.5 by 10 to the minus 5, divide it by 4 to get how many moles of oxygen there is going to be. That's your answer to part 2. Now the next question, the concentration of dissolved oxygen in the water in moles per litre. Okay, so when they ask a question like this, the concentration, it's not asking for a specific amount of moles. You can usually use this formula. So I'm going to use the titration, which is the molarity of the iodine, the volume of the iodine, over the number that's related to iodine in the chemical reaction, the molarity of the sodium thiosulfate, the volume of the sodium thiosulfate, and the number related to the sodium thiosulfate. Now these numbers down here, these letters down here, they are just as a guide for me to know which side relates to iodine, which side relates to the sodium thiosulfate, which are here in the reaction. So let's fill in what we can. So the molarity of the iodine, we don't know, so we're going to leave that blank. The volume of the iodine used was 200. And the number that's associated with iodine in the chemical reaction is 1. The molarity of the sodium thiosulfate, we've already worked out from previous parts of the question. And then the volume was the average titer, which is 6. And the number associated with it is 2 from the chemical reaction. If we maneuver those around, we're going to get the molarity of the iodine to be 1.875 by 10 to the minus 4 moles per litre of our iodine solution. So if we look over here now at the concentrations of oxygen, these are the ratios that we're given. So we're told that 4 moles of the sodium thiosulfate reacts with 1 mole of oxygen. We need to figure out how many moles then in terms of the ratio relates to this iodine that we've just figured out. So if you look back up here, it says 4 moles of the sodium thiosulfate, whereas in the reaction it just says 2 moles of sodium thiosulfate. So I want these two sentences to be able to link together so I can work out the iodine up here. So 4 moles of sodium thiosulfate. So I'm just going to multiply this line by 2. And that's going to turn into 2 here. This will turn into 4. This will turn into 4. And this will have a 2 in front of it. So now it does relate the 4 moles of sodium thiosulfate and the 4 moles of sodium thiosulfate. And I can see that the 4 moles of sodium thiosulfate will react with 2 moles of iodine. So I can put that there. So they're all of my reactants there in the terms of the ratio. Now the concentration of dissolved oxygen in the water in moles per litre. I have the concentration of the iodine in moles per litre. So I'm just going to put that in and slot it in here. So from that, I can now work out how much the oxygen should have. And I can see that's half of it, so I'm going to divide it by 2 because it's reacting in a 2-to-1 ratio. So I just take that number and divide it by 2. And that's the amount of the concentration of oxygen in moles per litre in the water. Now, if you want to do it a different way, we did work out, if we didn't want to work out this section here, we did work out already how many moles of oxygen were in the titration. So from back up here in this part 2, the number of moles of oxygen that released iodine in each titration. So we worked out that it was 1.875 by 10 to the minus 5 moles of oxygen in each titration. And each titration, there was 200 centimeters cubed. So we have the volume in 200 centimeters cubed. So if I want to just bring that up to moles per litre, there's 5 200 centimeters cubed in a litre. So I'm just going to take that number, 1.875 by 10 to the minus 4, and multiply it by 5. And I should get the exact same answer. So just by copying that is in 200 centimeters cubed, and I want to bring it up to a litre, you can do the question in a much simpler fashion, in 2 sentences rather than all of that. So now, the last one, the concentration of dissolved oxygen in the water in parts per million or milligrams per litre. Okay, so I have the molarity, so I've got the moles per litre. So the first step is to convert from moles into grams, then to milligrams, then to parts per million. So I'm going to use this formula. Number of moles equals mass over relative molecular mass, which will be the oxygen, which is 2 times 16, which is 32. So the number of moles we have is 9.375 by 10 to the minus 5 moles of oxygen in the water sample. We need to figure out the mass, and our relative molecular mass is 32. So moving that around, we can get the mass equals, just multiply these two numbers together, and we're going to get the mass then to be 3 by 10 to the minus 3 grams per litre. Or that looks like grams per litre, if you don't want it in scientific notation. So that means now, if you want to convert to milligrams, you just hop it back 3 spaces, and that's going to now be 3 milligrams per litre, or 3 parts per million. So you found the concentration of dissolved oxygen in the water is 3 parts per million. So looking back up at the original question, the concentration of at least 5 parts per million of dissolved oxygen in a water system is required to support a large and varied fish population. So based on that titration there, you can see that there's not sufficient amount of oxygen in that water supply. Okay, so we're going to look at the book question now. So again, if you want to pause, give a read through, we've now 3 calculations this time to look at. And I would suggest taking out the important parts of the information, trying to actually organize the question yourself, pull out the information and see where your starting point is for this type of question. Okay, so this is the information I've extracted. So I've set up 2 columns. The first is for the sample of water that was tested straight away, and the second column is for the sample of water that was tested after 5 days, kept at a constant temperature. So then I also looked and I saw that the sample was diluted, so I just wanted to make a note of that. I worked out the dilution factor by seeing how many times the 50 centimeters cubed was diluted into the 1,000, the litre. So the dilution factor is a factor 20. And I've also just made note that the answer needs to be in parts per million. So my last thing to look at now is this 3 chemical equations, just to work out any ratio that I might need to use. So all I do is I look along and I find out what is in the first reaction that's also in the second reaction here. So I can see that this chemical is the same as this chemical, but the numbers are different, and I just want them all to relate to each other So I can multiply this number by 2. That's going to change that number to 2. This one is going to change to a 4. This one will change to a 12. Might choose a different color to do this actually. Okay, so I just multiply that whole line by 2. And I'm going to again look at what is in this line, the second line, that is in the same as the third line. And I can see it's this iodine molecule here. And I have an iodine molecule here. But again, the numbers are different, so I'm going to have to multiply this line by 2. This is going to turn to a 2. This will turn to a 4. This will turn to a 4. And this will turn to a 2. So now I can set up another piece of information, which is the amount of oxygen that reacts with the iodine, that reacts with the sodium thiosulfate. And I can see that the oxygen number up here is 1, the iodine number is 2, and the sodium thiosulfate number is 4. So I have all of the moles in terms of how they react together for those 3 chemicals. So I should have all of the information needed to just go for the question. So let's just look at the question again. What exactly is it looking for? Calculate the amount of dissolved oxygen in each sample of water. So for the sample that's done straight away and the sample that's taken 5 days later, express your answers in parts per million. So we'll do the first part first, and then we'll look at this B.O.D part afterwards. Okay. So you're going to take a look at this chemical formula for the titration. And it's asking you to find the concentration of the dissolved oxygen in each sample of water. So we can go straight in, hopefully with this formula here, which is the molarity of the water, or you can say the oxygen if you want, the volume of the oxygen, and the number related to the oxygen, the molarity of the sodium thiosulfate with the volume of the thiosulfate and the number associated with sodium thiosulfate. So we can do the one that was done straight away, this titration that was done straight away. So I'm just going to put that up here, straight away, okay? So the molarity of the water, we don't know, or the oxygen is, we don't know, that's what we're trying to figure out. The volume of the water, or the oxygen there, was 300 centimeters cubed. That's what was used in the titration. And the number associated then with the oxygen is 1. The molarity of the sodium thiosulfate is 0.02. The volume that was used in the titration that was done straight away is 14.7. And then the number associated with sodium thiosulfate is 4. So maneuvering that equation around to find the molarity of the oxygen, then we're going to get an answer of 2.45 by 10 to the minus 4 moles per litre of oxygen. Now I can do it again for the second titration, which was after 5 days. Set up the exact same formula, but we're just going to input different values now. Okay, so we've calculated the molarity of oxygen in each sample. Okay, so you can see that from here, we need to change this moles per litre into parts per million. To do that, you need to go from moles per litre to grams per litre to milligrams straight into parts per million. So we're going to use this formula for both sides. Number of moles equals the mass over relative molecular mass. And we're going to do the exact same thing then over on the other side. Okay, so we have the number of moles. And then our relative molecular mass for oxygen is 32. And you're just going to work out the mass. So just maneuvering that equation around, we can work out what the mass is. Grams per litre. Okay, I'm just going to pause and fill out the other side. So I've that done now for both of them. I've got them all converted to grams per litre. And I'm just going to do it to milligrams now. So you take 3 steps back. So 7.84 milligrams per litre, which converts straight to parts per million. So 7.84 parts per million. 1, 2, 3. 2.56 milligrams per litre, or 2.56 parts per million. So now I've that part done. Calculate the amount of oxygen dissolved in each sample, express your answers in parts per million. Hence find the B.O.D of the water. So the B.O.D is the biochemical oxygen demand of the water. So you know we've titrated the water straight away and then after 5 days. That's to see what's the difference in the 2 dissolved oxygen levels and how much oxygen has been used up during this time and during the test. So all you have to do is look at the difference in the parts per million of the oxygen before and after the 5 days. So you're going to take 7.84, take away the 2.56, and you'll get 5.28 parts per million as the difference of the oxygen uptake, or how much oxygen we've lost within that time. Now it does want you to relate it to the whole water sample, and if you remember, we diluted it by 20. So to get a true representation of the water sample, we now need to multiply this by 20. So we're talking about the water sample, the original water sample, not just the amount that we made up. So it's 105.6 parts per million is the B.O.D of the water sample.